Hello and welcome to our lesson on similar figures. Now before we talk about similar figures, let's talk about congruent figures. So remember, congruent in geometry is another way of saying that measures are equal. So congruent figures are figures that have the same shape and the same size. So they are identical. Now similar figures have the same shape. So the same looking triangle or the same looking trapezoid, they look the same. However, they're not the same size. So one might be big, one might be small. And what we'll find with similar figures is here's an example of two similar figures. Notice they are the same shape, but they are different sizes. When we are identifying similar figures, we're going to use the little tilde. So looking in the lower right, we can say triangle ABC is similar to triangle DEF. They are similar. And how do we know that they're similar? Well, we know they're similar if their corresponding side lengths are proportional. So these side lengths, these corresponding side lengths are proportional. So A to B is proportional to D to E. B to C is proportional to E to F. Okay, so these side length ratios are proportional. Now to be the same shape, the angles need to be congruent. Those angle measures need to be congruent. So that is what makes it the same shape. And then the side lengths being proportional make it a different size, but yet keep it that same shape. So let's see if we can identify similar figures. So if we look at rectangle A, which one is similar to A? Rectangle B or rectangle C? Well, we know all the angle measures are congruent because they're all rectangles, so every angle measure is 90 degrees. So now we need to check to see if the side lengths are proportional. So let's look at rectangle A and B. And I always like to kind of think of this as new with the original. So the first one is always the original. The new one is what we're comparing it with. So I'm going to write my proportion and ratios as rectangle B over rectangle A. And I'm going to start with the lengths here at the bottom. So we have 6 for B and a length of 6 for A. And we want to know, is that proportional to the other side lengths, which are the widths here? So for rectangle B, it's 2 over 3. And clearly, 6 over 6 is not equivalent to 2 over 3. So these are not proportional, so it is not rectangle B. So it must be rectangle C, but let's just double check. Let's compare C to A. Looking at the lengths at the bottom, we have 4 to 6. We want to know, is that proportional with the widths on the side, 2 to 3? And I think we can clearly see that 4 6 is equivalent to 2/3. You could either do cross products, 4 times 3 is 12, 6 times 2 is 12, or simplify 4 6 to 2/3. All right, so the answer would be rectangle C is similar to rectangle A. Here's one for you to try. So which is similar to a rectangle that is 3 units long and 1 unit wide? So you might want to sketch a little rectangle on your paper that has a length of 3 and a width of 1. All right, so rectangle B is similar. If we look at the ratio, the lengths 3 to 6 is equivalent to the widths 1 to 2. And we can use these relationships to find missing values, in particular missing side lengths. So we can set up proportions and then solve those proportions to find the missing dimensions. And whenever I set it up, I always like to think of the one on the left as the original, the one on the right is the new, and set it up as new over original. So that's kind of how I like to set up my ratios. And I always like to put the ratio that has what I'm trying to find second. So I always like to do the known ratio first. So I'm going to do 9 over 6. That's the known ratio equals. Sorry. That's very common to do. I almost wrote 8 over x, but it's x is the new over 8. And now I need to solve this proportion. So I can do cross product. 6x is equal to 9 times 8, which is 72, and that's easy enough. Or I can see this can be simplified. 9/6 simplified is 3 halves. It's equal to x over 8. And I know that 2 times 4 is 8. So 3 times 4 tells me that x is equal to 12 meters. 3 times 4 is 12. Let's look at another example. This one I already wrote out to make things go quicker. So again, doing new over the original. The known lengths are 6 to 4. 6 to 4. And I want that to be equivalent to x over 8. This one scales easily. 4 times 2 is 8. 6 times 2 is 12. Now, I showed two triangles, but it works the same for pentagons, quadrilaterals, any two similar figures. So go ahead and give this one a try. All right, so you should get x is 4 feet. And one more with a quadrilateral. And x is 24 centimeters. Now, just as a note, as we learned before with proportions, there are 8 different ways to set up this proportion. So you could have actually set up a proportion using the same figure. So for example, we could have done 7 over 12 is equal to 14 over x. And that would work just as well. And actually, this proportion works nicely because 7 times 2 is 14, so 12 times 2 is 24. So just remember, there are many ways to set up your proportion. I kind of have a set method, so I always do it the same way. All right, here's one, a little word problem. So this one you'll probably want to use cross products after you set it up. All right, so the height here would be 3 inches. So 3.75 over 15 is equal to h over 12. Again, cross products and solve. All right, this next problem is one of my favorite examples. It's a triangle within a triangle. So a person standing 30 feet from a streetlight casts a shadow as shown. So let me label that. So here's the person. They are standing 30 feet from that streetlight. We want to know how many times taller is the streetlight than the person. So we need to figure out how tall this streetlight is. So this is our x value. Then once we figure out how tall that is, we can figure out how many times taller that is. And the thing to see here is we actually have two triangles. We have our first triangle here, our smaller triangle, and then we have our larger triangle here. And the smaller triangle is inside the larger triangle. But our proportions work the same. They are similar because all of these angle measures are the same and our side lengths will be proportional. So let's go ahead and set up our proportion. What are the known side lengths? Well, we know the base here. So for the smaller, let's use the smaller one as our known, the bigger one as our unknown. So this is our original, this is our new. So if we do new over our original, the original being the smaller one, we get our new value of the large triangle. Well, it's easy to just think that that is 30, but actually what is that base length? It's the 30 plus the 10, which is 40. So that's the number one mistake on these problems. So it's 40 over the original 10 is equal to the new big triangle is x over 6. And we need to solve this proportion. All right, so again, cross products, whatever you want. You can see that 40 over 10 is 4 over 1 equals x over 6. So then just scale up by 6. And we see that x is equal to 24. So we know that the height of this is 24 feet. the question is asking how many times taller is the street light. So 6 times what gives me 24, and that is obviously 4. Now if you needed to, you could do 24 divided by 6 is 4 for a trickier problem. So our final answer is 4 times taller. All right, so here's a similar problem. I just want you to find x on this one. We have a triangle inside a larger triangle, so set up your proportion and find x. All right, so I have 2 to 12. Those are my known ones, 2 to 12. And then we have 12 and x plus 2. Okay, so that's the tricky part, is this base length is x plus 2 all the way across. Now, you can do cross products, but I notice the numerators are both 2. So that means I can just set these 12 equal to x plus 2 and solve for x, and I get 10. So x would be 10. All right. So our last topic for today is something called a scale factor. So a scale factor is the ratio of corresponding side lengths from the new image to the old image, the pre-image of similar figures. So if we assume these two are similar figures, we can actually use either of the side lengths to find out our scale factor. So again, we want to do new over original, and that would be our image over our pre-image. And since we know they're similar, we know these side lengths are proportional. So I'm going to go ahead and just use 12 and 4 and simplify. So that turns into 3 to 1. So my scale factor is 3 to 1, or a lot of times you'll see it written as 3 to 1. Now, if you notice something, scale means we're changing the size, factor means we're multiplying. What is 3 over 1 simplified? It is simply 3. And what is 4 times 3? This side length, 4 times 3 equals 12. What is this 6 times our scale factor? That is 18, this side length. So factor, again, it means what you're multiplying. Scale is how much it is a changing of size. So the scale factor is what you multiply your original value to get the new value. Okay, so that's another way to think of it. Let's look at another example. So we have a pre-image to an image. So again, we can pick either side. These are both similar. So we're going to do new over original, which again is our image over our pre-image. Pick any side. This time I will just take the widths, because that's going to give me a simplified ratio right away, which is 2 to 3, which is equal, I'll just put or, written as 2 to 3. Now most of the time in online homework assignments, you'll see it written as a ratio using the colon format. But again, notice, since this is our scale factor, we should be able to multiply any dimension from the pre-image by the scale factor to get the new image's value. And sure enough, what is 3 times 2/3? That gives us our 2. And what is 6 times 2/3? That also gives us our side length of 4. So go ahead and try these two. All right, so for A, you get 1/3 or 1 to 3. And for B, you get 3/2 or 3 to 2. Notice 12 times 1/3 is 4. Notice 10 times 3/2 is 15. Another thing to note, if you're going from big to small, your scale factor should be less than 1. If you're going from small to big, your scale factor should be greater than 1. All right, that'll do it for today.